Okay, well, our talk today is by Tom Rippeth, who's Professor of Physical Physical Oceanography at Bangor University and a Fellow of the Learned Society of Wales and the Royal Met Society. He has a strong research interest in turbulence and mixing and involving the development of new techniques for their measurement. So his research has taken him to various parts of the world, including the UK waters, of course, and also the Arctic. One of his present interests, as he was just telling us, is the impact of mixing by turbulent wakes generated by tidal flow past floating wind farms. So today he's going to talk about the history, a little bit of ocean microstructure developments and insights. So over to you, Tom.
Thanks very much. Thanks for everybody for joining. I don't know what the weather's like where you are, but here in North Wales, we're sort of switching between being in a cloud and being in heavy rain. So not like 2 days ago when we were all enjoying the Aurora Borealis. So yeah, so I'm going to basically look at what got us to where we are today, probably with more relevance to shelf seas than the deep ocean, although I do make some deep ocean references, particularly thanks to Stuart Cunningham, who provided me with a very interesting paper which had a few diagrams in I was looking for and failing to find elsewhere. So thank you to Stuart. So this picture gives away some of the things we're going to talk about, really. This is actually just off the Menai Suspension Bridge, just outside of the Marine Science Labs in Menai Bridge a few weeks ago. And if you look at the water, it's very turbulent. And basically, ocean microstructure is all really about turbulence and what it does. So if we sort of go back to probably the earliest types of measurements that might lead us to think that there's something interesting going on, one of my favorites is actually the Halley calculations based on an eclipse that the Babylonians observed in 136 BC. So as this is a history group, I thought going back over 2,000 years might be something quite exciting to do. And the Babylonians, basically, their belief system was based on omens. And just as we want to predict weather and climate and things, the Babylonians wanted to predict omens to tell them when they were going to have severe weather events or famines or plagues or whatever. And in doing so, they made intricate observations of astronomy spanning some 1,000 years or so. And the worst of the omens that they could experience was actually an eclipse. So what they did was they made these observations and then they um, essentially fitted sine waves to them and were able to predict the risks of eclipses. And that sort of probably sat dormant for 1,500 years or so until the sort of Enlightenment and such, and people started thinking about the natural world and the way the natural world works. And the obvious thing is to first of all think about things that have some sort of cyclicity. And the most obvious things that have cyclicity, the things that go on above us in the sky, hence sort of the Babylonian interest, but also the sort of interest of later people in particular Sir Edmund Halley, who was Astronomer Royal. And what he did was he was aware of these Babylonian um, eclipse observations, and he tried to back calculate them. And in doing so, he found he could work out the exact timing of these um, eclipses. But what he also found out was that the eclipses didn't actually happen over Babylon. And this particularly 136-year BC eclipse actually was predicted to occur over Babylon, but actually it was predicted to occur over the UK, not Babylon. And that probably gave us the first real insight into the fact that the tides were doing something on the planet, because it's all to do with the drag imposed by tidal friction, very gradually slowing the Earth's rotation rate, and so increasing day length by about 2 milliseconds a century or something. And when you add up the million or so days, um, the 2 milliseconds over the million or so days between the Babylonian observation and Halley's calculation, that sort of predicts a 4 hour time difference, which is what could be used to explain Halley's prediction of the eclipse being over the UK and not over Babylon. So tides have attracted a lot of interest since then. And one of my favorite papers is a very local paper to us in Menai Bridge. And it's a paper by G.I. Taylor, or several papers by G.I. Taylor. And I should say that one of the most bizarre, precious series of papers in the Menai Bridge Library when I started doing the MSc there was actually the collected works of G.I. Taylor and John Simpson and Dave Bowers and others would regularly point us when we asked questions. Oh, yes, well, G.I. Taylor thought about that. Go and look at such and such a paper. And one of the things that interested me was tides and gulfs. And of course, this Irish Sea paper was a real classic there. And it was the one where Taylor calculated the direct input of energy to the tides from the gradient of the tidal generating force across the Irish Sea, showed it was basically negligible. He used the phases of the tidal current velocities and amplitudes to calculate the flux of tidal energy into the Irish Sea from outside, and showed that that actually balanced with tidal friction using a, um, a U cubed friction parameterization. So basically, what Taylor and others that followed him showed was that pretty much all of the dissipation, or about 70% of the dissipation, due to the tides pushing the moon away and the Earth slowing down, actually takes place in the shelf seas. So we've got a good source of turbulence, which is what we started off by looking at um, over the Menai suspension bridge a few minutes ago. Now, another interesting observation. So Nansen's always fascinated me because in his bid to get to the North Pole, he made some extremely interesting observations and some extremely insightful comment on those observations. And one of those observations was the fact that the sea ice, was actually drifting at about 20 or 40 degrees to the right of the wind direction. And his PhD student, Ekman, actually did some calculations to show why that was. And of course, that brought us to the Ekman spiral that we all learn, or we teach to our first year students. And in doing so, what he had to do was, he couldn't take molecular viscosity. He had to use a much, much larger viscosity to try and to be able to explain this drift that had been observed by Nansen. And that implies that there's actually something, turbulence in the water column, which is significantly increasing the viscosity to explain the motion. So we're starting to link dynamics into the sort of ideas of turbulence. And basically that brings us up to where I should say I would start getting interested. So just about 60 years ago I was born. So looking back at where we were 60 years ago, we're about 20 years on from Group W and the birth of modern predictive oceanography here in the UK. Ken Bowden had been out in Red Wolf Bay, just off Anglesey, and he'd been very carefully measuring Reynolds stresses in the water column and linking the tidal current profile shape essentially to the production of turbulent kinetic energy. So getting the energy out of the mean tidal flow into turbulent mixing. More generally, we were moving away from discrete bottle samples to actually using electronic profiling instruments. And as I'll show you, that greatly improved the resolution of what we're seeing. And in terms of oceanography, there were many, many conflicting theories going around, not least of which was on the formation of the ocean thermocline, or another way of thinking of that is maybe the nature of the meridional overturning circulation. And the two theories, so this Stuart was telling me about this paper at Christmas, and I found it really interesting that there's basically two theories. One is what we currently accept, which is essentially the sinking of the cold water in the polar regions is balanced by mixing down of heat at lower latitudes, although there's other sort of variants um, being added to that. And then there was an alternative back in the 60s, and it was a low mixing alternative, so it was associated with the development of subtropical gyres. And these theories were to get over something that's Sandstrom's theorem that basically said you because if you're making cold water at the poles, the ocean would fill up with cold water unless you found some way of getting heat from the surface down. And Walter Monk thought about that, and he derived something by thinking about the balance between sinking and mixing through a diffusion coefficient. He was able to estimate how much mixing that you would need to be able to balance that flow. So that was in the deep ocean. In the shelf seas, probably less talked about, but measurements were taking place, and there was a particular set of measurements that were made by a chap um, between 1908 and 1912 on Her Majesty's yacht, the Helga, which sailed out of Dublin. So it was before the Irish uprising. And this chap would sail around the Irish Sea about 4 times a year, I think February, May, August, and November. And he would make bottle samples at series of stations. And those series of stations, um, you can see examples of here. So the North Channel, this green um, series here is basically to the north of the Isle of Man. And you've you see that the dominant contour is quite interesting at this time with salinity. So people were more interested in salinity really than they were in temperature. But what he did note in August, and these profiles were from August, were that it's some in August in the Celtic Sea and in the Western Irish Sea. In this section here, the green section is the Western Irish Sea. You actually had some stratification forming. So it was seasonal. It was only there in August, and it didn't extend right across the Irish Sea. It was just part of the Irish Sea. And John Simpson actually went back there later with a CTD, and he made measurements across exactly the same section. And you can see here the temperature, and you can see the stratification on the left-hand side of the plot and mixing on the right-hand side of the plot. And that enabled them, because by that stage we not only understood more about the structure of the water column, rather than having 3 points, he had probably 100 points here from a lowered electronic instrument. He made inferences about mixing, and in particular used the position of this front, separating the seasonally stratified water from the mixed water, and the distribution of tidal mixing based on G.I. Taylor's um, energy balances to work out the balance point between stratification and tidal mixing. And I think this was really important in terms of understanding the role of tides in mixing globally, not just in the shelf seas, for two reasons. One reason is because people started thinking about shelf sea fronts across the globe after this point and pinpointing the positions of fronts and finding out that the link, the ratio, if you like, of the work done in mixing the water column and the energy available to do the mixing, in other words, the mixing efficiency, was, if you were comparing like with like, was the same wherever you are, whether it was on the Patagonian shelf, in the Bering Sea, in the South China Sea. So what we're seeing here is basically a quantitative link between um, the energy being dissipated by the tides and mixing in the water column. So another piece of work which sort of convinced people about this link actually happened around fjords, and it was a chap called Anders Stegebrand in Jutterberg, who carried out this work. And it was initially work he did in Oslo Fjord. And he basically worked out the flux of tidal energy into the fjord. So as G.I. Taylor had done for the Irish Sea, but across the entrance sill of a fjord. And then he looked at the I can't just don't know, get this out of the way. I can't see my full slide. He looked at profiles of temperature and salinity within the fjord, and if the bottom density decreased, he assumed that the water below sill level. So I've got an example here from the Clyde Sea, which is of huge historical significance, as I'll tell you about in a minute. So you've got a sill here at the entrance to the Clyde, then you've got this deep water behind. And below it, I made measurements in June and November 1990, we saw the warming of the deep water, the freshening of the deep water, and therefore the drop in density. Now that implies a flux of heat and fresh water downwards. And what Stigebrand did is he did that in about 40 or 50 fjords up the Norwegian coast and was able to show a relationship between the energy lost by the tide and the amount of mixing which was necessary to do this warming and freshening of the deep water. Now, the historical significance of these June 1990 measurements were these were probably some of the first would have been the first CDD profiles that Stuart Cunningham ever made. And how many has he made since? Maybe he can tell us later on in the talk. So we're getting pretty strong evidence that showing the tide is not only losing energy through friction, but that is performing a really important role in the shelf seas, and that there's some of it actually being dissipated in the deep ocean. And as we start to think about the deep ocean, it's probably worth thinking about how our um, improvement in measurement resolution really start to contribute to the understanding the deep ocean. So this is out of an article that Stuart gave me from Scientific American. This shows a profile made with a mercury bulb thermometer off the Scripps Oceanographic Institute. Then the middle one is a lowered electronic profiler, and then there's a blown up section there, which is just this pink section that you can see between 250 and 300 meters. And you can see all of a sudden you've gone from this smooth profile to a very rugged profile. So lots of fine structure in there. And if you go down further, you can see even more fine structure on scales of centimeters. And this was clearly of interest because if you look closely at this, you can see parts of the water column which, assuming the salinity is the same, are actually unstable. So they could actually be something of interest going on there in terms of fluxes of heat. Now, at this point, John Woods was getting involved, and there were his famous dye experiments in the Mediterranean. This was a picture taken of some dye that was dropped. So basically, a pellet full of dye was dropped, and you can see that it's not just a straight line, that the dye was being shifted by clearly shear flow in the velocity on scales of centimeters. And these measurements really got people speculating as to why you saw this microstructure. Was it interleaving of layers originating from different locations? Was it some sort of vertical transport processes, overturning of internal waves might be something we would think about in that way today, which are diffusing heat, salt, and momentum, resulting in the development of layers? Or was it actually due to double diffusive effects due to the fact that the salinity and the temperature have very different molecular diffusivities? So in the Arctic, for example, between the sort of warm intruding Atlantic water and the cold polar layer above, you see these really lovely staircases due to double diffusion. And we'll come on to that. But um, around the sort of late 60s, this discussion this was one of the sort of controversial discussions that was actually appears to have been going on in oceanography. And John Simpson and John Woods, and I think together with Steve Thorpe, headed off in the newly purchased ship, the Prince Madoc. This is the Prince Madoc that arrived in Menai Bridge about 1968. One of its first trips was actually up to Loch Ness. It went up through Neptune's staircase, as our latest Prince Madoc actually did this summer. So maybe for a later talk, we can get somebody interested in lakes to talk about that. But what they did was they went to drop this thing, the Proteus, off the back, and the Proteus basically measured very rapid changes in temperature. And the idea was that if you found very rapid changes in temperature, in other words, this temperature microstructure, which was being observed, for example, by Woods in the Mediterranean, in a freshwater lake where there's no salt, you could eliminate these double diffusive processes, salt fingering and double diffusion from the fine and microstructure that was being observed. So this was something they did. They observed this all of these stepping effects and all of these fine structure variations, and they were in a freshwater environment. So that essentially eliminated across vast parts of the ocean the fact that this could just be due to double diffusive processes. And this is where Steve Thorpe was starting to think about overturning due to internal waves breaking and and mixing type stuff there. So this basically suggested that if you could measure Richardson number, this is Simpson states, or Simpson Woods state in this paper, if you could measure Richardson number, gradient Richardson number with high enough resolution in the ocean, it would tell you where you'd have layers where there was mixing going together. So quite surprisingly, so this paper was published in Nature in 1977, and last time I checked, it only had 23 citations, which is quite remarkable because in my view, it certainly did change the way people were thinking about what we're observing in the ocean and get people to move in a different direction. What in modern day ref terms would be probably classed as an agenda setting paper. So through the 60s, or more through the 70s, particularly on the west coast of Canada and the US, there was a lot of work went into developing microstructure as a way of measuring turbulence. So building on these initial insights, but using velocity microstructure. And velocity microstructure was seen as the best way forward as opposed to temperature microstructure, because if you had a profiler that was falling at a reasonable fall speed, something like half a centimeter a second, so half a meter a second, something like that, then you would get a spectrum, a shear spectrum, which would have a turning point in it. And that would be well away from any noise that would be likely to occur from this thing as it wobbled, as it was going down, or because of electrical interference. Like, there's a 50 odd hertz spike there, which is probably related to electrical interference at the top end. And these profilers developed to be able to measure turbulence, and basically the way they work. So this is one. Well, I was going to say this is the one we have in Bangor. It's not actually one we have in Bangor because it went missing in the South Atlantic about 2 years ago. So for some reason the tether snapped and we lost it. But other ones exist in Bangor and elsewhere. And what you do is you drop it off the back of the ship. It has a constant fall rate, so it accelerates over about 5 or 10 meters, and it measures very rapidly the shear between a piezoelectric sensors, so like record needles down here, and the center of the instrument. So it gives you a shear estimate, and you build a time series of shear, and you can then transpose that into a space series if you assume that the time series is stationary, and then it gives you a shear spectra, which you can then integrate to give you a dissipation estimate. And these instruments, if you're wondering why it looks like a toilet brush with this big brush on it, that's just to regulate the fall speed and ensure that it falls at a constant rate, and it gives you a dissipation measurement. And the attraction of dissipation is it's the same in all directions, unlike the eddies that we saw in the Menai Straits earlier, which are largely 2D. So we're looking at the end of the turbulence journey as opposed to the larger scale eddies, which are probably doing the stirring and mixing, which are generated from the shear. So it gives us a good measure of where the mixing's taking place, so we can assume production and dissipation balance. And these measurements were deployed in the ocean around the same time that people were starting to do dye diffusion experiments. Now, the dye diffusion experiments were throwing up diffusivities that were far too small to explain the balance with the deep water formation in the polar regions. But when the dissipation measurements came in, and these are a series published by Kurt Polzin in '97, you can actually see much larger dissipation, just restricted. In this case, it's the Brazil Basin, restricted over the rough topography. And this gave you the idea that it's actually interaction between the flow and the topography driving internal waves, driving enhanced mixing. And they then went on to extend this to look at how this varied through the tidal cycle. Now, these profiles down to 5,000 meters, you can't use tethers because the instruments go too slow. So you drop the instrument and you get one profile, which makes it difficult to resolve things like the tide, for example, or inertial oscillations or whatever. But what they did was that they analyzed these measurements and they were able to show there was a springs neap cycle, which suggested that this higher dissipation was actually due to dissipation of tidal energy through internal waves being generated over rough topography, in this case across the meridional, across the mid-Atlantic ridge. So this hunt for dark mixing took one huge step forward at this point, thanks to these dissipation measurements using velocity microstructure. Now we've been making them in the shelf seas, which is much easier because it's shallow. So this was our first profiler, just being dropped off the back of the Prince Madoc. And these are some velocity shear measurements, temperature shear measurements, and we did, just for a bit of a laugh, we compared them from opposite sides of the world. So here we've got the black ones, which are from the Western Irish Sea, so thermal stratification. And then we've got the blue ones, which Jim Moom had collected on the Oregon Shelf in similar tidal conditions. So I think the point we're trying to make here is dissipation is the same wherever, Newton's laws of physics basically are the same wherever you're on the planet. Now, one of the things that we did quite early on when we started, well, when we sort of Bangor came back to measuring turbulence, we bought an instrument off the Canadians and decided to use it to look at dissipation either side of this tidal mixing front in the Western Irish Sea. And we made the measurements at two locations. One of them was at a location where we knew the tides were strong, so we got 0.8 centimeters a second and about 90 meters of water. And the dissipations were quite high, so we're up in so this is a log scale, and we're up in the yellows and the greens here. There's a strong tidal signal, so there's a strong dissipation around flood and a strong dissipation around maximum ebb, and then it falls away in between. If you actually integrate those and compare it to the sort of the Cairo UQ'd model that G.I. Taylor introduced us to, you can actually see that our integrated dissipations match the theory, which is always quite reassuring. And then when you move into the Western Irish Sea, much weaker tides, same water depth, and you can see that the bottom boundary layer, it doesn't penetrate right up the water column. It's only goes up to about 30 meters. You can see some higher dissipations close to the surface, and then you see a background here of about 10 to the -5, 10 to the -6 watts per meter cubed, which is about a decade above the instrument noise level. So it's a believable level from which you can work out fluxes. And the motivation for this was John Simpson was just getting into thinking about turbulence closure schemes that were being used in the new 3D generation of models that were coming out. And we used these measurements to basically test turbulence closure schemes that explicitly used dissipation, calculated dissipation as part of mixing. And we discovered that easily these schemes, without some sort of modification or fudge, were very poor at reproducing the dissipation in the middle of the water column. So we've got here the mean dissipation from the observations, the solid line, the dotted lines of the model. And this is a log scale. So in this case, with a Miller-Yamada closure scheme without any sort of fudge factors added, we're about 5 orders of magnitude too low in the middle of the water column. Now, the middle of the water column is quite important because, of course, that's where you mix the heat down or you mix the nutrients up or the carbon or whatever parameter that you're looking at. And one of the things I thought about was, well, if it's not the tide interacting with the seabed that's driving that, what is it? And as measurements um, became, particularly ADCP measurements became more and more common, we were able to suspend ADCPs in the middle of the water column and measure relatively fine velocity gradients, and we're able to show that basically the gradient Richardson number was about 1 in the thermocline. This is in the Western Irish Sea. We also showed in the North Sea, the Celtic Sea. Jen McKinnon in the US was starting to get similar measurements in the northeastern shelf off New England. And as it was about 1, we thought, well, it's marginally stable. All you need to do is to find a bit of extra shear and you'll get some mixing. And I went back to look at those original measurements we'd made off the Prismatic, remembering that the Prismatic was a very uncomfortable ship to be on in a storm, and that we'd actually had a storm just before we made the measurements in the Western Irish Sea. So we'd gone and sat in the Isle of Man for about 36 hours. And I compared the dissipations to some current meter measurements that we had out there. So we didn't have ADCPs moored on the seabed at that time, but we did have some current meters. And this is the shear estimate, the solid line, and this is the thermocline integrated dissipation. You can see there's a spike here, and the dissipation actually goes up by about 5 times. And you can imagine, you can see that with these are the hourly dissipations where there's a spike. There seems to be more dissipation going on. And I went back and looked at some time series from BODC, and you could see these regular bursts of spiking occurring in response to storms passing through. And that led us to think about inertial oscillations, driving thermocline mixing, and to develop a model that actually showed that the inertial oscillations could explain these higher levels of dissipation we're observing in the thermocline that because they hadn't obviously been captured because we'd set up a 1D model driven by the tides to look at the dissipation in that original 1996 paper. Now, all of this is of interest in terms of biogeochemistry because the shelf seas, these stratified shelf seas, are some of the most biologically productive marine ecosystems on the planet. And one of the reasons for that is because they're seasonally stratified. So the system completely mixes in the winter. It brings up a load of nutrients ready for the spring bloom. And then once the spring bloom has stripped out the surface layer nutrients, you see nutrients which are transported up through mixing across the thermocline. And we went to look at that. Well, we actually went to look at the eclipse in 1999, but under the guise of looking at mixing of nutrients. And these were some measurements that Jonathan Sharples published in Eleanor in 2001, where we'd made 24 hours worth of dissipation measurements. And we'd also done hourly CED profiles. So we were measuring chlorophyll, and we were also measuring nutrients from bottle samples. And what we saw was that at some point, chlorophyll started appearing in the bottom mixed layer. And this is where that green arrow is on the plot. You're getting all of this chlorophyll. It appears to be being mixed down. But if you looked at the velocity, so this is the velocity in the middle panel, it was actually around slack water, which seemed a bit strange. But what the dissipation measurements told us was, yeah, it's around slack water, but it takes time for the turbulence to be generated. There's a lag in turbulent generation higher up the water column. So there's a phase lag between the seabed and the thermocline. And I don't think we would have put those two things together if we'd not had the dissipation measurements, so the microstructure measurements at the same time. And in some more recent measurements, we've been worrying about oxygen being mixed down because one of the big threats to shelf seas is oxygen um, running out during the summer due to the decay of organic matter, which sinks. And this plot on the right, I won't go through all of the details of it, but it shows you the shear at three levels. So 35 meters is about the center, and then later on the top of the thermocline. 47 meters is at the bottom of the thermocline, and for the first third of the time series, 16 meters is actually the top of the thermocline. Now at the top here we have the surface wind stress in red, and we have in blue um, the tide, and it's just a tidal cycle average value of dissipation estimated from the tide there. So we've got springs, a big springs, a neaps, a smaller springs, a neaps. And what you can see is that the mixing at the bottom of the thermocline, so this bit that we're seeing here, is dominated by tidal shear. So the blue is tidal shear on this plot. That shear around the inertial frequency, i.e. that due to inertial oscillations, is pretty negligible. You move up into the thermocline, you see that the inertial shear is playing a role, particularly around this period here, and the tidal um, shear plays some role. And then when you move higher up the water column, so for this first third of this time series, it's actually inertial shear that's driving the flux up from the top of the thermocline, and it's actually tidal shear which is driving the flux down. Now, in terms of oxygen, this is really significant because this subsurface chlorophyll maximum that we're observing here is actually producing a lot of oxygen. So you've got a huge oversaturation of oxygen here. And this is showing us that it's the storminess is taking that oxygen to the surface and outgassing it, and the tides are mixing that down. So you've got this very fine balance in the thermocline, which is explaining the Richardson number one, but it's also playing an important role in terms of biogeochemical cycling. So just to sort of finish off with, I'm going to talk a bit about some more recent stuff in the Arctic, but I'm going to go back to Nansen and a profile he took in the Arctic using Nansen bottles in 1895. Now, you'll have probably all seen this picture in Ocean Challenge, and it shows basically that the Atlantic water has probably warmed significantly, and there's other measurements that confirm it has warmed significantly since the time of Nansen's initial measurements in 1895. So there's a CTD profile. This was taken during one of Youngji Len's Changing Arctic Ocean projects in 2018, and these bottle samples were Nansen's bottle samples in 1895. And the reason that we got asked to go and make measurements of turbulence in the Arctic was around 2007, we saw a massive decline in Arctic sea ice, and there was lots of headlines on about Arctic meltdown and Arctic sea ice is at a tipping point and all the rest of it. And there was quite a lot of interest, particularly from Sheldon Bacon in his in the National Oceanography Centre, in whether this big decline was actually being driven by the fact that there's more heat escaping out the Atlantic water and getting to the surface and melting ice. And I should say Stuart Turner had done a calculation and he'd shown that there was enough heat actually entering the Arctic Ocean from the Atlantic Ocean. And this was around this time of this minimum to melt the Arctic sea ice about 3 times over. So there was a lot of excitement, and the obvious way to test that was to make microstructure measurements. And we actually got the opportunity to make microstructure measurements on no fewer than 4 occasions. We joined Russian ships to make measurements in the Kara Sea and the East Siberian and the shelf break region and the deep ocean beyond that. We joined a Canadian icebreaker to make measurements in the Canada Basin, and we joined the JCR to make measurements north of Svalbard. So in this region here. Now, the first region we went to was this region, which is to the north of Svalbard and in the deep ocean. Um, we collected all these profiles, and at this point at Bangor, we'd just taken on a new postdoc called Young Jean Len, who I'm sure you've all come across, who'd recently moved over from Scripps, and she had the job of working up the microstructure measurements, which we believe are the first ever microstructure measurements to have been made up here. Working up the microstructure measurements to look at the rate at which heat was being mixed up from that intruding Atlantic water towards the sea ice. And it only took her a few weeks of looking at the measurements to say, look, guys, there isn't any turbulence. The instrument's just giving us noise. And what's more, we can see all these lovely double diffusive staircases at the top of the Atlantic water. So her first paper for this region was actually all about the heat flux due to double diffusive processes moving heat towards the surface across the thermocline separating the Atlantic water. Well, it's not really a thermocline because, of course, the density variation due to the temperature change at those depths is actually very small. It's actually the salt difference which is giving the density difference, but you get this heat flux upwards due to these double diffusive fluxes. She showed that, and she also compared the profiles, evolving profiles, and showed that there wasn't actually enough of a flux of heat to explain the changes that were observed in those profiles. Now, it could have been variations in the amount of heat and salt that were coming in through the Atlantic that were explaining the different transects, the CED profiles and different transects, how they're varying. Or it could have been that there was some mixing that we were just missing at this point. So anyway, when we got to 2012, we went out there in the Canada Basin, and that was when the all-time low summer sea ice was observed. And it was because there was an almighty storm came charging across the Arctic, smashing up the ice in its wake. And basically, by the time we got out to make measurements here, there was no ice in the Canada Basin, and the Canadians said that this was totally unprecedented. They were making measurements there every year for about 40 years or so. They'd never seen anything like this. And it gave us the ideal opportunity to test out the ideas that were floating around at the time, that the less ice that we have, the more wind mixing we have, and therefore the quicker the heat will get mixed up, so the more the ice will go back. And we actually found, yeah, there was more wind mixing, but it was restricted to the top 50 or 60 meters or so. And the double diffusive staircases at the top of the Atlantic water were not interrupted at all by the extra wind mixing. So being Bangor, I suppose, and their sort of history of tidal mixing, the next thing to think about was, well, are the tides important in providing energy towards mixing? And one of the things that Matthias Green at Bangor does is he works with the likes of Gary Egbert and the Oregon team, looking at where the tides dissipate energy in the global ocean in the current day, but also going way back in the past. And he was using altimeter data to work out, to basically do what G.I. Taylor did, but using altimeter to work out dissipation. I said, can you do this for the Arctic? So I think he spent about 2 hours, and he came out with this profile moving round from Svalbard right round the shelf break, round the Arctic Ocean, and back out to the Fram Strait. And he showed basically what our dissipation measurements across this temperature region of temperature change at the top of the Atlantic water was showing into qualitatively. In other words, lots of dissipation going on to the north of Svalbard, very little dissipation going on in terms of the tide in the region where we made those first measurements that Young had worked up. Slightly more going on in the Canada Basin, and potentially a lot more going on around here in this area to the north of Greenland, which is always encrusted in ice. I should say if you put on where ice normally shrinks back to, you'll find that we've managed to cover most of the area where there's not normally ice in the summer at this point. And given the current geopolitical situation, I think it's going to be a while before anybody actually gets back to add more measurements, particularly in this area of interest here. So we showed that the tide was important in mixing in certain areas of the Arctic, which is something people had really not. It really wasn't on the agenda probably until we published this paper. Um, but we hadn't explained those initial measurements. And in 2018, they were making measurements again. I wasn't really involved in this. This was in Young's Changing Arctic Ocean project, and also part of Mosaic and Lance and Legacy cruisers. They were actually collected thousands of dissipation profiles in this region here, which was the region to the north of Siberia, where we thought there was no dissipation going on at all. And there was actually a postdoc in the Alfred Wegener who was working these up, Kiki Schultz. And I remember at a Gordon conference, she was presenting this, and she said she checked thousands of dissipation profiles, and there's a load of them plotted here, and she only found one that was interesting. Well, that's not quite true. I think she found three that were interesting. And you can see here, you've basically got noise here. So this was a poorer resolution instrument than the one we use. This was an what's called an MSS profile she was using. So all she was seeing was noise in all of these profiles, but there was three profiles where you're actually two or three orders of magnitude above the noise level in measuring dissipation. In this region where we've shown that the tide isn't any sort of contributor to mixing. And that got us to think about, well, if it's not coming from the tide, where is it coming from? And she went back and looked at ADCP data, and she actually found out there's a really strong barotropic downslope current, 50 centimeters a second current. And if it didn't come from the tide, where did it come from? Well, around the same time, people were thinking about the Arctic, and they were thinking about the generation of continental shelf waves. And people had started to talk about the fact that you could observe continental shelf waves that are basically they're generated by the water being piled up at the coastline. In our case, since for Siberia, it would be sort of in the Barents Sea. That relaxes, it then rushes offshore when the storms pass through. The water gets piled up by the storm, rushes offshore when the storm passes through. Because the Earth's rotating, it ends up forming a wave because vorticity turns it back onto the shelf when it goes down the slope. And it forms, as it runs down the slope, something called an unsteady lee wave, which was the mechanism we'd come up with for dissipating the tidal energy, because you can't really generate freely propagating linear waves, internal waves at the tidal frequency at the Arctic latitude. So we had to rely on this unsteady lee wave. And it was a really exciting result in quite a few people's view, because basically these continental shelf storms, they're generated by storms. These continental shelf waves are generated by storms at lower latitudes. So they're generated by essentially low pressure systems coming across the Atlantic and going across the Barents Sea, and then the energy propagates into the Arctic Ocean. And what Kiki said was, well, does ice affect that? And she did a plot where she identified these events from ADCP data, and she showed, yeah, ice does have a big effect. So there's very few in the winter. I think she only got 3 in the winter off Siberia in the Eurasian basin, but she got lots of them during the ice-free periods. Now, anybody that knows about storms in the northern North Sea and the Barents Sea and places knows there's a lot more storms in the winter than there are in the summer. But in terms of the energy getting round there and being able to do mixing, it's only getting round there when there's much less ice. And these lines just show the percentage of ice cover going from 100% down to 0%, and then the storms, or rather the continental shelf waves, are shown as these stars. And then you've got different years when there's different levels of ice decline in this sector of the Arctic Ocean. So this gave us a mechanism which could be affected by global climate change through sea ice retreat, through and changing storm tracks to mix heat up in the Arctic Ocean and melt ice away. So obviously, there's a lot more different ways to measure turbulence coming online now, talking about measuring microstructure of alga floats, these things. And the one I'm just going to give a quick advert for is the one that we've been working on Bangor over the last 20 or so years, which is called the structure function method, which can be applied from ADCPs that you buy off the shelf and can be stuck onto moorings and can be used to measure turbulence. And this was, so Hurricane Katia, these were some measurements we made in the Clyde Sea at about 40 meters in this case. Red measurements are VMP measurements. Black measurements are dissipation estimates from the ADCP. You can see pretty good agreements here, here, and here between the VMP and the ADCP. And you will see that as the storm comes through, you measure dissipations which are 3 orders of magnitude higher, when obviously the Prince-Matic was tied up in Ardrossan at the time, and we were all sitting in the pub, the storm lashing on the windows, and the ADCP was returning turbulence measurements. And we were then able to go out after the storm had gone and validate them using the VMP. So lots of exciting opportunities to use turbulence to try and enhance our understanding of not only the dynamics of the ocean, but also the movement of important things like nutrients, carbon, heat, and then fresh water in the ocean. And I shall finish on that point there. Okay, and happy to take questions.
Thanks, Tom. Well, this thing is set up as a meeting, so anybody's got to do is to unmute themselves and then fire away, but don't all go at once. So, any questions for Tom?
Phil, can you hear me at all?
Yeah, okay, Stuart, fire away.
All right. Oh, Tom, thanks very much. I really enjoyed the talk a lot. Still so much to do in the world of turbulence and thermohaline circulation. Anyway, as this is a history session, I thought I would mention a really nice book which was written in 1900 by Professor William Hastie, who was in the physics department at Glasgow. Well, actually, he was a professor of divinity, but he wrote a really nice book about an essay that Immanuel Kant had written in 1754 for the Berlin Academy of Sciences. And the book was called Discovery of the Retardation of the Rotation of the Earth. Now, back then, they would just announce there'd be a prize and people could submit anything. And Immanuel Kant, probably much well known as a philosopher, but of course, he did a lot of work in earth sciences and he really thought
Right.
about the tides in response to the change in rotation rate of the Earth. So I thought people might be interested to maybe look that up and see about it because it's one of the very early works on that. And I know you were suggesting there was maybe something earlier, which, well, I personally hadn't been aware of. But the thing I really wanted to mention was that Immanuel Kant, of course, he has very strong Scottish antecedents. His grandfather emigrated from Scotland, of course, so everything good is coming from Scotland. And he went out to Prussia and then made his name in Germany. But
Excellent.
for some reason, and I can't quite figure out why, because not a lot of links about why suddenly people became interested in this retardation problem. But especially in the Kant essay, there's no kind of hint about or introduction as to why he picked up on the idea. But from what you said, maybe the idea had been floating in philosophical circles before that. Anyway, he wrote this essay and won a prize for trying to describe the effect of Earth's tides on that.
Oh, you must send a link to that. I mean,
Yeah.
I just picked out individual cases there just to sort of set the scene really, but I know George Darwin worried about this problem and various other people worried about this problem as well. So I think it was quite a big talking point in the late 19th century amongst natural scientists. I mean, there are probably other people online that know more about that than me, to be honest.
Okay, thanks, Stuart. I see John and Angela have unmuted themselves. So, John, do you want to go first? If you
No, I didn't. I didn't particularly want to say anything. I just
okay,
pressed the button.
how about you, Angela? Have you got
No,
something?
no, I wasn't. No, no. I just really enjoyed it. So varied as well.
Thanks.
Well, who was the guy again who 1910 went on the Helga around the Irish Sea?
There's a chap called
Um,
Donald Matthews,
oh, never heard of
and
him.
he worked for the Fisheries Institute in Dublin.
Right.
And an interesting um, extension of that was that the Helga was actually used to suppress nationalist forces during the Dublin uprising. Was it 1916 or 1919 or something?
Oh, was that the boat that sailed up the Liffey and bombarded
I think so,
the
yeah.
forecourts or whatever? Yeah.
Yeah, it was certainly it was certainly involved in that.
Okay. Right. So, has somebody else got a question for Tom? Still gone quiet.
I mean,
So,
just a comment. I think, when I started going to see deep sea in the late mid '60s, we basically were in this transition from water bottles to profilers, and the profilers were extremely unreliable, particularly for salinity. But there were people actually trying to guess, particularly in the Mediterranean water, and even trying to decide that there was stratification by looking at the salinities between the first samples and the last samples drawn off a water bottle, because they thought you might be able to actually detect stratification within an individual bottle. I don't think it ever actually worked.
No. Yeah, so talking about the unreliability, I remember John Simpson saying to me when he started his PhD with Ken Bowden at Liverpool, he was sent off to sea, and the advice Ken gave him was he better take a soldering iron. I was thinking, what's that for? But
Well,
I mean,
well,
certainly over the years on the Malik with VMP profilers, and particularly the old fly profile, we all learned to solder in quite arduous conditions sometimes around the top of Arran and places because things would get broken when the instrument bounced off the seabed.
hmm.
But yeah,
Well, the other real problem was that most of the early salinity sensors were inductive sensors, so they A, they were physically large, and B, they were affected by how you set the frame up or whether you had a water bottle attached to it, and
right.
it was completely inconsistent.
Yeah. But I
But
mean, the reason I sort of got into this, well, into the contents of this talk really, it's just the fact that we make observations and we understand things. And when I teach the students, I talk about, Newton. He set down a set of laws that govern the universe, but then Einstein came along and challenged them by making things very heavy and very fast and all the rest of it. And oceanography is the same, really, because it depends what you can measure, really.
Mhm.
That's the limit of science, is what
Right.
you can measure,
Yeah.
because anything beyond that, you can't validate and you can't test. And, you look at oceanography and it's all happened, or a lot of interesting stuff's happened, certainly within the lifetimes of the people on this call, maybe
Mm.
not the youngsters like Stuart and I should say, but there's so much has happened over that period in the post-war period that I don't know, it's a good time for us all to review it really and just get a really good grasp of how
Well,
the subjects move forward.
I think you raise an interesting point, because documenting the various steps that are along the way between where we were, say, in 1965, 66, and where we were by 1990, I think there are huge steps forward there.
Yeah, no, absolutely.
I think it's very interesting, Tom. I mean, you focus a bit more on continental kind of shelves, but you were also in the Arctic. But I do think it's still like a cutting edge area for our understanding of the large scale global ocean circulation. I mean, trying to understand where the thermohaline circulation is closed by the upward mixing of heat and so on. Really, it's not just about the large scale. I mean, it happens in very narrow boundary currents where flows pass over sills and so on. And it's a real challenge for modeling. And a large scale example is that models have difficulty creating the vertical profile of the Atlantic overturning circulation, for example. But
Yeah.
it's often set in very, very narrow boundary regions. And these regions are often the very last cell in a model, for example, the one next to the bathymetry, where they're trying to parameterize stuff and do physics in that very last cell. And I do think there's still an enormous challenge, both for observationalists and the modelers, to figure out where in the world we're doing all this mixing along these very fine scales, which speak to the largest scales we have.
I mean, absolutely, Stuart. And so to go back, so this paper here with the Stigerbrand one, that was probably the main text of my thesis, and that is totally relevant to the overturning circulation and where the mixing element of it takes place, because you've got all of these fjords up the coast of Norway. They're all different sizes, right? Some are long, some are short, and all the rest of it. Yet you get this really good fit between the amount of energy going in and the amount of mixing that takes place. Now that tells you that most of the mixing is taking place within a relatively short distance from the sill. And we went out and we made measurements in a fjord with Stigerbrand in, I think it was 2000 or 2001 or something. And we went up and down this fjord for about a week, making measurements at about 8 stations, and we found that 70% of the energy was dissipated within 1 kilometer of the sill. Now, there's no reason why that should be any difference in the deep ocean, right? Now, in a fjord, which is 20 kilometers long, measuring within 1 kilometer is something that's quite easy to do. In the deep ocean, you know, getting your instrument down to make one profile close to that source is going to be difficult. To get repeated profiles, which you need if it's the tide generating it, because it's not a constant input of energy because the tide is varying, is really, really difficult. And that's where I think, this ADCP technology comes in, because it allows long time series. And we actually did manage to get a whole winter of measurements in the North Atlantic and the base of the surface mix layer, really, using an ADCP, and the dissipation measurements really gave us some interesting insights into the mixing processes there. So I think, you're totally right. There's an awful lot to learn, and it's a lot of it's linked into the fact that most of the dissipation occurs very close to topography, and that's the reason why the diffusion diffusivity estimates didn't match those that Monk had come up with that were needed to balance the deep water formation measurements, because of course they're integrating over huge basins, whereas the dissipation, the mixing is happening very, very close to the topography. And a fjord is a brilliant demonstration of that. And Mark Innell has got some very nice papers, and also Lars Onneberg, where we've made measurements of dissipation in fjords, which show that.
Okay.
Thank you.
Thanks, Tom. I guess we have to end at some point. I'll just mention, for those of you still here, that the next talk carries on a little bit like from this. It's about by Kees Kramer, about the bathythermograph and the rise and decline of that technique. And that's on the 18th of February. Okay, so thanks again, Tom. I'm going to press the stop recording now.